Okay, so where we there at the last time, so we were trying to explore a generalization of vertex cover as a degree 1 rule for the vertex cover. Okay, and before we ended, we realized one of the following things. Okay, so what did we realize? You have all the videos, so access, so you can go back and look at it. That's perfectly fine. Okay. Okay. So what were we looking at? We said that if the following situation arises, I just gave you a very nice example, is that suppose I have some set of vertices here, okay, and right, all kind of situation is there, okay, right, and we were trying to find what is a situation when we will be and all of you we knew that because it is a generalization of degree 1 rule, this set of vertices form an independent set, right. This is what we decided. And what was the situation when I told you that we must pick all these vertices from this in our solution? What was this? What was the reason to take this, guys?
Because there was a matching saturating.
Yes. So what we saw last time is that there is a matching. Look at this. Here is a matching. Here is a matching. Okay. Here is a matching. Okay. Here is a matching. Here is a matching. Okay. Now look at this matching. Right. Notice that if I have a matching of 5, what can I say about this? Does form a lower bound on the vertex cover, right? Right. Any minimum vertex cover, right, is at least greater than equal to max matching, right? Because at least you have to cover those edges, if not anything else, right? So this is, but what we saw that okay, I need to cover these edges. Now, if I pick these vertices, right, there could be edges here. I'm not saying, but what else is not there? There are no edges from here to here. Let's try to build what all is not there. Like we shouldn't be expecting, because if it is a generalization of degree 1 rule, I mean their neighbors are just here, right? So you do not have such kind of edges, right, in the graph, right? So graph, if I think of this, then if I, whatever you want to call it, say h, if I delete h from the graph, what is the property? These guys are isolated vertices and they will be deleted. Okay. Now, and we said, look, if that seems to be, if that is the case, then it appears that from this side, because of this red matching, we are guaranteed to have at least one vertex each from this red edges, right? We have to pick at least one vertex. Maybe any vertex cover picks, maybe more, but we can show that there exists a vertex cover which picks everything in the edge, right? Okay. So now let's try. So like this is a situation if arises, then we can apply some reduction rule. Now let's write down what will this situation mean. When will I say that such situation arises? Okay. So what should be the rule? You understand what I mean? Look, I mean we said, right, what was the prerequisitive rule, right? We said if degree of v is greater than equal to k plus 1, then g minus v k minus 1, right? So similarly, what this if statement should be to take care of this rule, right? So what should we say? So basically, let's call it, so this rule, if you notice, I have a graph G and an integer k. Now vertex set of G is some partition into some 3 sets, right? So let's call this C, H, R, okay? So vertex set is partitioned into partitioned, right? This is one. What is the property, another property we have here? What is another property? There exists a matching, saturating H into C. So this is my C and this. And what is the third property? There is no edge between vertices in C and R, okay, or in other word, H is a separator, right? H separates C from R, okay. So H is a separator separating C from R, okay. So basically this is a let's call this rule as whatever this rule is called. It is basically degree 1 rule on steroid. Okay. 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 So what I'm saying, if given this, if this property are satisfied, then we have the following rule. What is the rule? Then we are saying G minus H. Let's delete H from my graph and decrease my parameter by K minus H, right? Okay. Let's first prove there are two things. How will we find an opportunity to apply this rule? Checking a degree 1 vertex was easy. Checking a vertex of degree K plus 1 was easy, right? But how to find such a partition satisfying this property? Not clear. If a graph could have such partition, but we don't know how to find it, right? So we will look into the algorithmic question in a minute. But suppose if we did find such a partition, then is this rule correct, first of all? Okay, you understand my point? Okay. So what do I need to prove? Okay, I need to prove.
One more property to prove that C is independent.
You're right. C is right. C is an independent set.
Why is it a degree 1 rule?
I didn't write degree 1 rule.
Why is the 1 rule?
This is basically degree 1 rule on steroid. I'm not trying this degree 1 rule. Because we started with what? This is what it is, right? This goes, right? Now, what is the property? Why it is going? It is going because there is a matching that saturates this, right? So your C is a single vertex or all this vertex, right? H is this vertex and the rest is everything else, right? Now, I have many things, but the properties remain the same, right? Whatever the property we used for the correctness of the proof of degree 1 rule, that is exactly the same set of properties we need to prove. We need to use to prove the correctness of this rule. This is why. I mean, you can call it something else if you don't like it. In my head, it's a degree 1 rule, okay? Because it just exports the idea of degree 1 rule in a much more general case. But like, idea is this only, right? I mean, this is not an idea, this is an idea, right? This is a manifestation of idea in a different situation. That's it. I mean, whatever you feel comfortable with, okay? But we reach this stage by thinking about degree 1 rule and then trying to see where all we can apply, what kind of generalization of degree 1 rule we can apply and do something better. So this is how we reach. So, okay. Now the lemma which I want to prove, what is the lemma? Correctness lemma we want to prove. What is the correctness lemma we want to prove? Is the following, is that G comma K is a yes instance if and only if G minus H, K minus H is a yes instance. Which direction is easy of the proof? One direction is literally trivial. I think
K minus H to G comma K.
yes, that's obvious, okay? Because look, now look at this, right? Look at the backward direction. S be a vertex covered of size K minus mod H for G minus H, right? So now this S doesn't cover what edges? All those edges which are adjacent to a vertex in H. Now, if I add S plus H, what is the size of S plus H? S plus H covers every edge, right, in G, of course. And what is the size of this? S plus mod H, K minus mod H plus mod H, K, right? So forward direction is literally obvious. Okay. Okay. So what may be a non-obvious is a forward direction. Okay. Okay. So forward direction. Let's draw smaller picture and prove the correctness. Okay. Okay. So here is an H. Here is an I. Okay. Here is a matching that saturates H. Okay. Matching, saturating H, and here is the rest. Okay. The rest shouldn't be that big. I call this. Okay. Okay. So let's start. Let S be a vertex cover of G. Let S be a vertex cover of G of size at most k. Okay. Now, S minus C union H plus H, let S prime equal to this. Okay. First, what is the size of S prime? Right? What is the size of S prime? Is S, how much from C union H, how many vertices will you remove from S? Right? Because we have a matching of size H, okay, like S prime is upper bounded by how much? At least mod H, right? Why? Because matching of size H between C and H, here, this matching, right? So from this matching, you have to pick at least, maybe you are picking one vertex from here. Maybe you are picking one vertex from here. Maybe you are picking this vertex, this vertex, this vertex. But you are at least picking one vertex from each of the matching, right? So when I delete vertices from C union H, I am definitely deleting at least H vertices, right? Maybe more, because maybe I am picking more vertices, I don't know. And what am I adding? I am adding back all H. So I am definitely deleting this, adding this. So this is definitely a size is at most k. Okay. Now look at any edge, right? Look at any edge. Okay. Now, and maybe, okay. So now look at any edge. So, yes. Matching H into C. There is a matching between H and C, where every vertex in H, it's saturated. There is no vertex here which is not saturated. That's what it means, H into C. Matching, one endpoint is in H, the other endpoint is in C. That's it, nothing more. Okay. Now, claim, this is obvious, but let's prove it anyway. Claim, S prime is a vertex cover of C. Does anybody has any doubt about this? Right? So only vertex, what did I delete from S? What did I delete from S? Right? Deleted the vertices from C. The only vertices which I deleted from C, from S, look, S was a vertex cover, right? S is a vertex cover. Right? F is a vertex cover. All of you agree? Now, from S, let's delete C. Some edges might be uncovered, right? Now what happens after this situation? Some edges might be uncovered, right? Okay, uncovered adjacent to C, right? Now I also deleted H from this, okay? Now what happened? Now after this situation, some edges might be uncovered, uncovered adjacent to either H or C, right? Look, imagine, right? These edges, these vertices were covering some edges. Now you decided to remove them from the vertex cover. What edges are not covered? Those which are adjacent to this. Now what did I added? We added H, right? So definitely all the edges which were adjacent to H are covered, right? So after this stage, what happens? Only edges that might be uncovered are adjacent to C, right? But what do we know about C? Every edge adjacent to C is also adjacent to H. Done. There's nothing more to show. Right? So just follow the inequality and you are all there, right? So I first deleted C, some edges now, every edge was covered with S by definition. I deleted some vertices in C. I said, no, you are not going to be part of my vertex cover. Some edges becomes uncovered. Who? The people whom I have removed. So those were adjacent to C. Then I decided to remove some more vertices from I. So some more edges becomes uncovered. Who? Those adjacent to vertices which I have removed. Now I put back something. So what? I removed H and I put back H, right? So definitely H is being completely taken care of. Now something might be uncovered which are adjacent to C, but every edge in C is also adjacent to H. So you are done, right? So now this is where we use the fact that C is like a degree 1 vertex. Everything which C can cover, H can cover, its neighbors can cover, right? What is H? Another thing which if you notice is that n of C is exactly equal to H, right? So this is exactly why I call it degree 1 rule, right? So I have picked up into my solution everything which is neighbor to some set of vertices, right? Okay. So this is a formal proof. Now the question is, how do we find such decomposition? Okay. So to be able to apply this rule, I want to say that, look, if my graph has some such property, then I can do this. Okay. Okay. Any questions so far? Okay. So in fact, this has a name. This is called crown rule. Okay. Okay. So when I saw first time in my life crown rule, I never understood why will someone think about it. At least it was very counterintuitive to me that suddenly there's a jump. So suppose if I did not tell you from degree 1, I told you just this as a rule, and this is very valid rule, I can prove this to you. But it is not absolutely not clear, like why would I think about coming up with such a rule? So what I want to prove now is how to find such things. So I want to say either graph is small. So this is the important thing. Look, maybe finding this decomposition in general may be very hard, right? If you want to find which maximizes cardinality of H, could be very hard question. But I want to say that, look, if the graph, so this is the kind of nature of lemmas or theorems we prove in this, is that if graph seems too big, then I should be able to find such a situation easily, right? Only reason I am not able to find such a situation is because graph has become too small that all these things are quite closely related to each other, right? Now, let's make this formal. Okay? So what I want to say, okay? So now, why it is called crown rule? Because it's like, think of this way, no? This is like a crown of a, this is like a body, head, crown. Okay. Right? This is how the crown of a king sits, no? Like, this is exactly what it is called crown. Okay? So it has a name, it is actually called crown rule. Okay, but it's a very powerful rule, right? I mean, if I find really large H in one go, we are able to remove everything. Okay. Okay, so we proved correctness. Now let's try to prove. So what will we say is the following. Okay. So here is my lemma. I do not remember the statement correctly, but let's see. In polynomial time, okay, given gk, okay, we will decide the following, or will conclude the following. We will conclude one of the following. Okay. So, what? So, in polynomial time given gk, I will give you a polynomial time algorithm which will tell you one of these things. Okay. G has a matching size k plus 1, it can tell you this, or it will tell you that it will tell you that G has a matching of size k plus 1. Vertex set of G is at most 3k, it can tell you one of these things, or find C H R decomposition. Okay? This is it. So, in polynomial time, I will be able to tell you one of these things. Now, notice what happens. If my algorithm returned you this, what can you say? Huh? What can you say? If I told you, hey, here is a matching of size k plus 1, what can I say? G comma k is a no instance. Okay, if I returned you this, then what can you say? You say, okay, fine, take your graph. Okay. Then you return G comma k, and what is the size of G? Vertex set of G is upper bounded by 3k. Vertex set of G is upper bounded by 3k. I am not saying the instance size is bounded by 3k. Please return gk with vertex set being at most 3k. Maybe the number of edges could be quadratic, I have no clue. All I am saying to you, the number of vertices is bounded by 3k, number of edges could be quadratic, right? You have a click, right, on k vertices with k square edges. Okay. And if I have this, what will I do? Apply reduction rule. If I find such a decomposition, what can I do? Apply reduction rule, what we call crown rule. All good? So, if once we prove this lemma, okay, once we prove this lemma, all are okay, we are done. Okay. So, let us try to prove this lemma. It is not, I think last time someone was saying some nice things, now we will see those nice things. Okay. We will also assume one thing, G has no isolated vertex, okay? Otherwise we could anyway delete it. So, G has non-isolated vertices, this is important for us. Okay. First step, what should I do? Find a maximal matching M, find a maximal, not even maximum, find a maximal matching M okay. So, if M is at least k plus 1, I stop, I return this answer. Okay. Okay. So, now we are in the case, what is the case we are in? Which implies what is the vertex set of M at most 2k. So, let us look at, this is my vertex set of M. What is this set of vertices? What is this? What is the property of G minus Vm? Huh? It is an independent set. Agreed? So now we are getting closer to our decomposition, right? Right? Why? Because this is why. If m is greater than or equal to k plus 1, you are done. Because Vm is a vertex cover of size at most 2k. Okay? Okay. Okay. So now it's an independent set. Let's call it I. I want to keep my red color. This is I. Now, there is no isolated vertex. So, every vertex has some edge like this, right? Right? Okay. Let H be a bipartite graph with bipartition. Let's call it, okay, with bipartition Vm comma I. Okay. So, I am only worried about, forget about the edges inside this. Look at just this. Think of this as a bipartite graph. I am going to, so basically I am going to call a bipartite graph which only consists of this I and this vertex set and the edges among them. I just forget the edges here for now. Okay. So, what is the property? H is a subgraph of G. Okay. So, what is this? H. Okay. And what is H set? So, edge of H is all edges in G with one endpoint. For completeness, let me write it in Vm, other in I. Okay. So, what is the property? H is a subgraph of G. Right? This is true, right? Because I took the same vertex set and I only kept some of the edges in my graph. So, this is just okay. Now, what I want to say, let M star be a maximum matching in H. M star be a maximum matching in H. I can find this in poly time. Okay. Okay. I mean, you have to believe me that we can find a maximum size matching in bipartite graph or in general graph in poly time. I am sure most of you don't know how to find this in general graph, but like in bipartite graph I am quite sure all of you know. Okay. Okay. Now, what can I say if M star is large? If M star is greater than or equal to k plus 1, then what can I say? What did we do? Can we say no? Right? Then you are still in this case. Right? Like maybe when I was finding a maximum matching, I couldn't extend it anymore. But now in this part, I find a maximum matching which just turns out to be large. Okay? Okay. If this return G has a matching of size at least k plus 1. Okay. So, now we assume that M star had size at most k. This is important for us. Now, find two things. Let W be a minimum vertex cover of H. We can find this, by the way, again in poly time, right? And the property is, this is where someone was saying last time, yes, this is where we will use in the proof. So, what is, there is something famous theorem in graph theory which is called conic theorem. What does it say? In bipartite graph, maximum matching is equal to minimum vertex cover. Okay. So, what is a agreed? Okay. Okay. So, let us go in this picture and let us draw M star. This is my M star. Okay. Now, I found this W. Okay. So, where could W be? It could be here. Can W contain both endpoints of my black edge? Because look, size of M star is exactly equal to size of W. So, from every maximum matching edge, it is going to pick exactly one vertex, otherwise it is not a vertex cover. So, it could be like this, it could be like this, it could be like this, it could be like this. Okay. So, I want to have one easy situation first. Suppose everyone is here, no, here, here, right. If W intersection H is empty, it could be the case, right. Then what is the size of I? What is the size of I? Is at most k, because there is no isolated vertex, right. So, every vertex has at least one edge incident to. If there is in this bipartite graph, from this bipartition, if you did not pick any vertex, right, then you better have the case that if total number of vertices here is bounded by k, otherwise you will have one vertex and that edge, who will take care of that edge? Okay. So, if this happens, then the size of I is upper bounded by k, and then are we done again, right? We are done again, because now what is the size of vertex set of G is equal to vertex set of M plus I, which is 2k plus k at most 3k, right. So, now we are in this situation. Okay. So, what we know that W intersection H, so now we have to only deal with the case when W intersection H is not empty, right. Okay. 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 So, pictures are important. Okay. And now we know, so suppose this is what it is. Okay. Now we know that W intersection H is not equal to empty set. Okay. So, now we are in the case that what is the case when W intersection H is not equal to empty. Let oh sorry, no, so then you should say, I am not saying that, I am just saying vertex set of M, my bad, sorry. Okay. W intersection VM is not equal. Let oh maybe, oh god, wait, this is just such a horrible notation. Okay. Let G prime a bipartite graph with this, okay, E of G prime, G prime, G prime, G prime. Okay. You will see why I did whatever I did. Okay. 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 Now, I wanted to use head as W intersection VM. Okay. So, what is my head? H is in this picture, what is my H? Is this one. And what is my C? The matching partners. And what is my C? Matching partner of vertices in H in M star. Right? Agreed? So, in this picture, they are this. Okay? So, this is my crown. Okay? This is my crown. Okay. Now, what is my rest? What is my rest? Rest is rest. Rest is vertex set of G minus H union C. Bad. Matching partner. Matching partner. Matching partner. No neighbors. It's up to me what I define, no? Okay. I have to just show that it has all the properties. That's it. Wait, I'll show it. Hmm? You can. I mean, there's nothing harm in it, but like, I mean, the proof will be unnecessary, we may say. Why do you want to do that? There's no other reason you could take. I think you can take. Okay. Okay. So let me see what happens now. Okay. So now let's fold it up, right? So this is HC, and all these are, and these are R. Okay. Now what we have to show for the property? So property was that, look at C, there is a matching that saturates C into H. Sorry, there is a matching H that saturates into C. Okay. But the first property was C is an independent set. C is a subset of an independent set, right? C is a subset of I, implies C is an independent set. So this is done. Secondly, there exists a matching saturating H into C by construction. Okay? What is not clear? Why there is no edge? We have to also prove that H separates C from R. Third and most important property is H separates C from R. Definitely, where are the edges of C? Starting from C, where are the edges? Look, all the edges adjacent to any vertex in C is in this bipartite. First of all, notice by a construction from H separates C from R in G. Okay. So every edge adjacent to C, adjacent to a vertex V in C, is present in G prime by our construction, right? How did we took? We said look at this independent set and look at all the edges that are crossing, right? So there is no edges here anyway. So this is, so every edge adjacent to a vertex V in C is present in G. Okay. So now what does it mean? Okay. So suppose you had here green colored, and suppose he had some edge like this going, right, to some other vertex. Who covers this edge? Because what was H? Every vertex in W which was present here. So now if you have such an edge and you said that W is a vertex covered, W can't pick this vertex anyway because W can pick exactly one vertex from this matching edges. So if you have such a red edge, what happens then? Who takes care of this? And that's it. Okay? Which implies if this edge is adjacent to some vertex not in H, then it contradicts that W is a vertex cover of G prime. That's it. So, it is quite clever. And now, why did I not take neighbor of V? You understand? If this is a guy, I do not know, maybe there is someone else who is taking care of him. So, how can I say something about it? Right?
For that also.
I need more arguments. Why should I make more arguments than required?
But then the same thing will happen, like if there is a neighbor of H and I, and that neighbor has a vertex to a remaining vertex, so that edge will not.
Yeah, but like, why should I argue so much? You get my point? You can make an argument, but like, it just makes life little bit more. You have to write 1 or 2 argument line more. But yes, I tell you, right? Because that is because look at these guys, right? No, wait. What's the problem? Suppose if we had this, then what happens? But that is not what we are trying to say, no? That is not a separator then, right? Then this set is not a separator for this. Okay. There could be some argument here, but like at least I don't see. At least I don't see now. Okay. So now, what is polynomial time? This is very polynomial time algorithm, right? So it's like it will run in m root n time because you need m root n time to find a maximum matching in a bipartite graph, right? And the reason why I did not want to use say maximum matching in the beginning, because then I have to tell you how to find a maximum matching in general graph, which I didn't want to. Okay, so I started with a maximal matching, which I can find greedily. Find one, delete all the edges which are adjacent to this, find another one, so on and so forth. So I found a maximal matching. If it is large, I am in the first case. So it is small, then I consider this bipartite graph G prime, where I found a maximum matching as well as minimum vertex cover. Now, because of Koenig's theorem, I know that maximum matching is equal to minimum vertex cover. So from my matching edges, exactly one vertex from the vertex cover is there. Now I look at this, I say, hey, is every vertex cover is in the I side, then the graph is already small. We are done. If not, then there are some vertices from my vertex cover in the non-I side. I look at those vertices and look at the edges which are adjacent to them, okay? And that I just look at those neighbors, call them C, call this head, and the remaining is your rest, and we prove that this is the right decomposition. Okay. So is that okay with everybody up there? Is that fine? People online?
Yes.
Okay. Okay. So once we have this theorem, we are very happy, right? Now, okay. So I'm going to remove this proof, okay? Okay. I think now the whole proof is on the board, more or less. Okay, I don't know if they are, but I want to keep this statement, okay? Okay. Okay. So there are, so this certainly implies now that we have a kernel or whatever you want for vertex covered with 3k and number of edges at most. We have not reduced the number of edges. Okay. But like once you have 3k, I don't have to apply other rules, right? I mean, I know that if I have just 3k vertices, the number of edges are 3k, choose 2 at most, so I didn't do anything. Okay. But there is a clever implementation of this rule, slightly clever implementation of this rule, and that will make you, it can reduce the size. So, let us try to have a slightly clever implementation of this rule. Rule remains the same, by the way. But for that, we have to take a detour. Okay. So, now we will see okay. I would say a better implementation. Okay. Okay. So, now we will take a detour. And we will write a LP for this. Okay. Do you know how to write a LP for minimum vertex cover? First of all, how many of you know linear programming? Everybody seems to. Okay. So, what we are going to have is that for every vertex v in Vg, okay, we are going to have a variable xv. Okay. Now, first let us write an ILP for this, and then we will write LP for this. Okay. Okay. And now, suppose I wanted to write an integer linear programming. Okay. Okay. Then what is my goal? My goal is to minimize the number of vertices that I will take into my vertex cover. So, what is my constraint? So, xv, what is the meaning of this? Xv is going to take value 0 and 1. 1 means select into a vertex cover. 0 means do not select into vertex cover. Okay. So, now if I write this, this definitely means that you want to minimize the number of variables which are going to set to 1. Okay. What is my constraint? What is the constraint they should satisfy? That the constraint is that from every edge, one of the endpoint must be selected. So, that immediately tells me that for every u comma v in edge, xu plus xv should be at least 1. And what we know that for all v in Vg, xu is in 0 comma 1. Okay. Notice that finding a vertex cover of size minimum size is same as solving this integer linear programming. Okay. So, can you solve this in polytan? No, right, because if the vertex cover is hard, then so is this problem is hard. So, ILP is way more harder than any of these specific problems that we can think of, because we can recast many problems in combinatorial optimization as this. And why it is called linear programming? Constraints. But what about optimization function? Maybe we can have a constraint. So, here what happens is that even my optimization function is linear, my constraints are linear. Sometimes we have constraint, we have like optimization function which could be quadratic or cubic or something, and constraint could still be linear. So, they are like different kind of program with different, or you could also have this which is not linear and this which is not linear, and people try to solve it. Okay. So, in approximation world there are such kind of programs which does this. Like for example, if you try to write a LP for max cut, it becomes a bit difficult, but what you are able to write is slightly something very different, which is like quadratic kind of program. Okay. Okay. But so, this is hard, but what is easy is when I relax. Okay. So, now I am going to relax this condition. Okay. Relax. I am not telling that xv takes value 0 and 1. So, I said okay, for v in Vg, xv can take any value greater than or equal to 0, any rational value greater than or equal to 0. Okay. So, now I have relaxed this condition by demanding that it only takes either 0 and 1 to something that is irrational. Okay. Now, this relaxed thing is called linear programming. Okay. This is beyond this course to teach you how to solve linear programming, but LP can be solved in polynomial time. Okay. Even when, but if so, let me look here. How many constraints do we have? How many constraints? As many as number of edges, no? Okay. But in many situations, the number of constraints we will have is very exponential. So you can't write down them all, right? But even in those some of the situation, you can solve LP. Okay. So how does, like, those are basically called LP where you have a separation oracle. What is meaning of separation oracle? So I am not going to my this LP, this I am not going to give the whole program. I will give him the optimization function and I will say this guy will tell, hey, is this your feasible LP solution? But I should be able to verify it and say, yes, it is a feasible LP solution, okay? Or it is not a feasible LP solution. If it is not a feasible LP solution, then I should be able to give this algorithm a constraint which is not feasible, give it to him, that is it. So, this is what I mean by separation oracle. So, what is algorithm going to tell you? Algorithm is going to say, hey, I think this is your feasible solution. And what is my role as a oracle or as an algorithmist is to take this, verify it that it is indeed a feasible solution, and if it is not a feasible solution, output a constraint that is not satisfied and give it to that LP solver. Okay. Now, that LP solver will take this, do some hard work, come up with another feasible solution or claim that, hey, is this a feasible solution? It comes back to this and gives it. Okay. Now, this iterative process goes on for a lot of time, but then what will the natural question will be? I mean, I have exponentially many constraints. Is it going exponentially many times? No. Every time you give this, in some sense, among all the possible feasible solutions which the algorithm can have, it does some sort of halving. So, this only goes polynomially many steps in the or logarithmically many number of steps in the constraints. Okay. Okay. There are like some, but the most important thing is that, like, don't go into that details, but at least to be able to, I'll give you a very good example. Suppose I would have been writing it the LP, if I was writing this LP where my objective was not to hit edges, but to hit all cycles of my graph. Then what will be my constraints? For all C in this summation, but how many cycles a graph can have? Exponentially many, right? But if I gave you some potential feasible solution even in LP, right, and you have to check, is there a cycle with value at least, like, which is there a, find a min weight cycle. If the min weight cycle has weight less than 1, you know this cycle is not satisfied, I can give it. So now you gave me some half, 1/3 something, right? LP gave, oh, I think this is your feasible LP solution for your feedback vertex set. Okay. What is my job? My job is to check that the min weight cycle has weight at least 1, right? And then I know how to find a min weight cycle in a graph, right? So if the min weight cycle is less than 1, then I say, hey, no, your solution is not feasible. Look at this cycle, you have not satisfied this constraint, right? And if min weight cycle has weight greater than or equal to 1, then I know that the feasible solution which this LP solver is telling me is right. So what implies that even though feedback vertex set have many constraints, right, we will be able to solve this LP in polytime. Okay. So just keep these things in mind, right? And for several things, so this is all that boils down to that you write your LP and you have to show that, okay, you can solve, given this feasible solution, given a potential feasible solution, test, and if fails, provide a constraint which is not satisfied. Okay. But in our case, it is very easy, it does it. Okay. Okay. Now, so let's just solve this LP. Okay, we solve this LP. So, p time, okay, and explain to what it means by p time. Okay. Here it is very easy, right? If someone gave you some fractional solution, just for every year check if that weight is at most 1 or not. Okay. Anyway, so now we have xv in this. Okay. Now we partition them into 3 parts. Okay. You see some interesting property immediately coming up. Okay. So, I'm on purpose I am going to write those. Okay. V, what is the meaning of I? I wrote on purpose I because I should mean somehow independent set. Is it clear that this is an independent set? Because how can you have an edge between 2 vertices in I? Look at V and look at W, right? Now, what is if they had an edge? What is the constraint? xv plus xw is at least 1. But this is xv is less than half, w is less than half. Can they sum up to 1? So, this is definitely an independent set. So, this is why the symbol I. Okay. Okay. I. Okay. Let's call it. Okay. Just to make more meaningful symbols. Okay. Agree? Okay. Notice if I take V half and V greater than or equal to half, that forms a vertex cover, because that is. What will be the size of these two, if you think for a minute? Okay, we'll get there. Think about it though. Okay. Now, here's the world. V half where his neighbors are. Tell me, where are V half neighbors are? Can they have neighbor in V half? No, right? Because because this is a strictly less than half, this is equal to half, this is still not going to make it more than half. So, are you seeing some separation already? It appears that here where the crown should be, it appears here where the edge should be, and definitely this and some other vertices should be rest, right? Okay, and you can prove this. Okay, but I'm not going to prove this. I'm going to prove something. It's just directly a reduction rule. What I'm going to prove to you that there exists an optimum solution containing V greater than or equal to half. Everything V half, there exists an optimum solution containing this whole thing. So I can actually treat, this is my H, this is C, and this is R in one shot. Okay, or rather, I mean, we can try, but like maybe we will succeed. We can try to show, if we can show there exists a matching that saturates H into C, then we are done. If we can show there exists a matching that saturates H into C, then we are done, because then we can apply our crown rule and we are done. Okay. Okay. So here's an exercise for you. Okay. Maybe it will come out from the proof. What is my exercise? It's a fun exercise. Okay. So fun exercise is show that there exists a matching saturating H into C. Okay? You should be able to show this. It's very like the reason why I'm not going into this, or maybe we have to go because you might have to. So how will you show there exists a matching that saturates H into C? Okay, let's try. Let's see if, I mean, what will happen. It's 20 minutes, right? Let's see. Okay. Does anybody knows what will happen if there is no matching that saturates H into C? So basically when I say H into C, like you only worry about the bipartite graph. You don't have to worry about the edges here because we are only talk. So what will happen? Did you teach them Hall's theorem? Okay, fine. This is why I was not getting there. But you might need to use some Hall's theorem. What is the Hall's theorem? That there's a, imagine that you have a big set here with small neighbor here. You can't have matching that saturates this into this, right? And this is a if and only if condition, right? So if there is something this, then we could do some fun thing. Okay. So do you want me to do that? Yeah. I think I will ended up proving anyway that. So but like okay, fine. Let's see. Okay. So let me tell you a canonical proof. Okay. This is slightly non-canonical proof which I am asking you to do, but there is some simple. Let me give you some canonical proof. Okay. So what is I want to show? I want to say there exists, and this is not proved. This is something which was proved in 1970s by Nemhauser and Trotter, like when they were doing this polytope for vertex covered matching polytopes. It is proved there in 1972. Okay. So it has nothing to do with parameterized complexity of this. This is basically pure combinatorial optimization. So what I want to show, here's the lemma. Let's see if I can prove. There exists an optimal solution S such that S contains V greater than or equal to half and contain inside, and if it contains V greater than or equal to half, what it means? It shouldn't contain V less than or equal to half because then it becomes independent set. Why will you, like this, all the edges are here, okay, and union V half, okay. So if this is what's our canonical solution? You start with S, and what should you do? You start with any optimum size, right? S is a vertex cover of minimum size. Okay, there exists an optimum or minimum sized solution. So what should I do now? S minus all the vertices of V half, and I add all vertices of right. This is what I want to do. This is all that I want to do, right? So I deleted some vertices, I added some vertices, right? I think this is like this is not right. Okay, so let's say, just to make life a little bit more. So suppose my S looks like this. S consists of say this vertices, and some this vertices. Suppose. Okay. Now what I am saying to you is that let's call this S out. This is like out of S, and what is this? S in, right? So basically by this I mean from S you take out S in and you add S out, okay? This is what it is, right? Now if S out is less than equal to S in, then there is absolutely no problem, right? Right? If, so let us call this S prime. So, if then S prime is less than equal to S, and we are all good. The problem is when cardinality of S out is more than cardinality of S in, right? So, these people are more than these people. Agreed? Okay. So, if this happens, okay, if this happens, let us try to reduce. So, what I am going to do now, if this is the case, okay. So, now what I am going to do is the following. Here it is and here it is, right. Now, I am going to increase every variable in S in by some epsilon, if I can do, okay. Okay. Going to decrease every variable in S out by same epsilon, right. Decrease and increase and decrease. So, let us write it correctly, otherwise decrease, increase. And now I do this, and what else do I want to do? Maintain this, maintain feasibility, okay, maintaining feasibility. Then what happens? Suppose O was summation of x v, right. Now what will be O prime? O prime will be all those, look at, in O prime I do not change the values of this, I do not change value of this, I do not change value of this, right, but I change the value of this and I change the value of this. So, O prime is going to be how much? O minus what I am subtracting? I am subtracting all these guys, right, epsilon times S out people, right, and what am I going to add? Epsilon times S in people. Now, in the situation we are in, S out is strictly greater than S in, right. So, what is the property of O prime? Because of this, O prime is going to be less than equal to O, contradiction that LP solved it optimally, contradiction that LP solved it optimally, right. Is that fine? So, this is our goal. So, if we are able to implement, right, if we are able to implement this, then we are happy. What is that? We said, look, if this is the case, then we will be able to find a small epsilon such that every variable is out, I will decrease this, and every variable S in, I will increase it, and that is it. Now, my question is, can you do this without changing feasibility? Okay. So, let us try to understand that why we should be able to do it. Notice one thing, okay, but another thing, decrease, but still being greater than half, okay, by some epsilon, still being less than half, okay, that is another property. So, now suppose if we are able to do this, now notice what happens. Look at any edge, let's look at the feasibility. Will anything happen to this edge here? Nothing will happen, because I did not change anything anyway, nothing. So, the only thing which could happen is that edges which are adjacent to this, but nothing will happen to, but something could happen to this edge, no? Because now maybe there was some quantity here, right? There's some quantity here. You get my point? So this, I mean, we have to be careful here, right? Okay. So this problem, like we will solve this problem. So let's just find that if we decrease this and don't do anything to this set of this, then something could happen. Okay. Okay. And anyway, nothing will happen here. Nothing will like no problem here, right? No, all this are no problem because still everything is more than half, so no problem. This is the only problematic edge. Why? You might ask, but okay, nothing will change here. But what about edges here? Will there be any edge here? No. I increase plus epsilon, I decrease minus epsilon, so they will compensate for each other. So only problematic edges are these edges. Do you agree? These are problematic edges, right? So if we can choose an epsilon in a way that there is no problem, we are good. You understand the question? You understand what we need to do? Like suppose I am going to increase the values of this, decrease the value of this by some quantity epsilon, increase the value of epsilon, every quantity here by epsilon, and still being less than half, greater than half. Now look at this edge. Maybe this plus this was at least 1, but now that you decrease this value, it could go down, right? Right? So you have to choose epsilon appropriately. You know, like choose any epsilon is not going to work. We have to show that an epsilon exists that will not create any problem for us. Okay? Right? Because decreasing this and still maintaining the fact that we are strictly greater than half has absolutely no bearing on feasibility of these edges here, right? And what about this edges? Well, this edges can have problem, but no, because in this you are increasing by plus epsilon, in this you are decreasing by plus epsilon, right? So for example, if you had an edge uv, so what is going to happen? This is now going to become xu plus epsilon, right? And other is xb minus epsilon, right? And this is greater than or equal to a1 anyway. So no issue, okay? And an edge between this and this, absolutely no issue. You have only increased, right? So the problem edges are, okay? So what are my problem edges? Let's write down. Problem edges between S out and C minus or let's say I have been using V less than half minus S in. So these are the edges which could have problem. Okay. Now let's try to show that we will not have such problems and then we will be good. Okay. 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 So for each edge, okay, let's call this edges between this and this. Let's call this problem edges. Okay. Problem edges. Okay. Now let's. Where should I write? I think I should leave this, right? Okay. Okay. I think this much space should suffice. Okay. Now notice, look at problem edges. Okay. Problem edges are, suppose uv is a problem edge. Okay. Okay. Now look at xu. So u is in whatever this is called. Okay. This side. Can I give some name to this? What name should we give it to it? I prime. Okay. Is in I prime and v is in your S out. Okay. Now you have xu plus xv, right? Which edges? Why can't there be an edge like this? Let's think about it.
I thought
What? Which blue portion?
The shaded blue and
No. S in is this, no? Yeah. I am only talking about edges between this. Why can't I have an edges? Okay, but that's, can I have such edges?
Yeah, so the blue shaded region where the solution is.
Okay, so the problem is, okay, so I think Caesar. So first of all, notice, okay, then there's something more funky happening here. Okay, let me think for a minute. Let me think for a minute. Okay. I think she's right. Okay. So look at this. Can you have such edges at all? Can you have the whatever problem edges did I write? Can you have such a problem edges at all? No. Why can't you have? Because look, then who is covering this edge, right? Because S out is not part of the vertex cover, and this is not part of the vertex cover. So basically, no edge in P exists. Okay, so this is basically vacuum. Otherwise, you are dead. Okay, so now I want to understand. Okay. Okay, fine. But we know that if we decrease this epsilon and increase this epsilon, then nothing will happen. But why does some epsilon which is greater than 0 exist? Okay, maybe all you can do is epsilon equal to 0, then you get nothing here, right? Need to show epsilon greater than 0 exists. Okay, otherwise there is absolutely no issue in this algorithm. Okay, the yes.
Decrease the variables this S out.
Yeah, we have to do.
Edges the S out to this V equal to half.
Meaning?
This can decrease.
No, I told you, right? I am still maintaining the fact that everyone is greater than half. Everyone is greater than half here. Even after a decrease, they are still greater than half. This is important, right? Okay. So what can I all have to look? Since I am going to increase, the only edges. So this, because you are decreasing, this edges could have affected, but there are no edges here. This edges nothing affects because I am still maintaining the fact that they are greater than half. The only thing so when I do this, and nothing will change here anyway because you are only going to increase this value. But this can affect, right? Why? I mean, if you choose epsilon, nothing will affect. But like, why does non-zero epsilon exist? Otherwise, this we cannot have. We said that O prime is strictly less than O, right? For that, we need to show that epsilon strictly positive exists. Do you agree? Right? Because, I mean, maybe if you choose epsilon equal to 0, nothing will, you can't say this. Okay. Okay. So now let's look at the edges which are adjacent to this. Okay. Now, this is strictly greater than half. This is strictly less than half, right? So now look at u and v here, u, v. Okay. So now look at xu and look at xv. I know this is greater than equal to 1, right? I know this is strictly less than half, right? So there is something, and this is, what do we know? This is strictly greater than half, right? So all I am saying, what is the small quantity can I decrease? Is there, what is a portion of small quantity that I can decrease from here, here and here, so that this is still greater than equal to 1? And such epsilon exists for this inequality, right? Why? Because look, this is strictly less than half, this is strictly greater than half, right? Choose some quantity, like, which is like, suppose this is like, suppose xu was 0.25, right? And xv is 0.75, right? How much scope do I have to decrease here? I can say I can actually take any number between 0.4999 from starting from 0.25, right? And whatever I add here, 0.24, I can also decrease 0.24 and nothing will happen, right? So because they are this, there is range of epsilon here. Okay, there is a range of epsilon that you can take. For every inequality, there is a range of epsilon. Choose the range of epsilon which is minimum and take that quantity. That's it. Right? So because XU, this is why we need it. It is strictly less than half, and this is strictly greater than half. You have a range, right? So you can at least slightly increase this, slightly decrease this. Rationals are closed, reals are closed, whatever. So rationals are closed. So you can always, between any two interval, you can find a number which is larger, right? So of course I'm using the fact that, okay. So all I'm trying to look at XU and XV, you have a range of potential epsilon. For every this thing, you have a range of epsilon. For everything, you have a range of epsilon. Choose the range which is minimum and choose any number between that. That is going to work for everybody. That's it. So this is what tells us that there exists an epsilon which is strictly positive, which we can decrease from here, and we can, which we can decrease from S out and increase from S in, and still maintain feasibility. And this epsilon is strictly greater than 0. Okay? Okay, all good? Okay. So then we are done, right? What we are done, then what we have shown, that there exists an optimum solution that contains all of this, and it is contained inside this, right? So you apply this reduction rule. So what will be my reduction rule now? Okay. So once we prove this, what's the reduction rule? Rule is very simple, no? Right? What is our rule? We are very powerful rule. Okay? We are not yet done. We are done with, almost done. What's the rule? G comma K, right? First of all, if greater than K, say no, right? Else what will we do? G minus, I mean, you don't even care. That's it. And the correctness follows because of this lemma. There exists an optimum solution containing this, right? So you take that solution, delete it, then nothing will happen. So this is a perfectly fine lemma. Okay. What should I rub? Okay, let me rub this. Okay. So after this rule is not applicable, what happens? When rule is not applicable, okay, and no degree 0 vertices, okay, then what happens? What happens? V greater than equal to half is definitely empty. If V greater than equal to half, this is also empty. What is left? V half. V xv equal to half. So what can I say? What is the size of V half? Okay. What do you know? Look at the linear programming solution. It is less than equal to what? Integer linear programming solution, because here I am allowing relaxation. So it can only become smaller compared to this. Okay. Now what is LP? What did every variable takes here? Half, right? So if I am what is my summation of xv, v in half, right? This is less than equal to ILP, which is less than equal to what? Our solution size, which is equal to k. So what is the summation of xv, v in half less than equal to k? This implies half times cardinality of v half, right? Should be less than equal to k. Do you agree to this? There is nothing. So that implies v half is less than equal to 2k. Otherwise, so what does it mean? If v half is more than 2k, you say no, right? So we will have another rule here. Okay. What's the rule? Add. If v half is more than 2k, say no, and done. That's it. Right. So what we are able to do? We are able to come up with kernel for vertex cover with size 2k, with number of vertices being 2k and number of edges being order k square. Okay. And we will prove at some point of time the number of edges we can't delete. Okay. I will give you a non algorithmic proof next time why k square seems easy, or okay. So here's my graph theory question to you people. Okay. Again, think. Okay. Why there's a relation? Okay. So why? So what we are able to achieve by now, okay, is the following. And let me write down my exercise, and then we will leave. Okay. So what did we achieve? Kernel for vertex covered with 2k vertices, and how many edges we were able to get down to? Because look, we could first get down, reduce the edges, and then, so it was how much? 2k square by 3, right? Look, we could apply first the edge reduction rule and then apply this vertex reduction rule. How does it matter? Okay. Okay. So this is what. But now I want to say, here's my exercise. I want to see if you can think of this. My exercise is very simple. G is k critical for vertex covered, okay, if for all okay, if for okay, if for all E in G, okay, G minus E has a vertex covered of size at most k minus 1. Okay. So, I am going to G is k critical for vertex cover. If for all E in G, if I delete an edge, vertex cover drops. Okay. So, this is critical, like in the sense that, okay, my question is, how many edges, what is the maximum number of edges possible? What is maximum number of edges, I need an upper bound, possible in a k critical graph G for vertex cover. Is the question clear? Right? I am telling you that, look, I want to come with an upper bound. Of course, n square edges, don't. But like, can you come with something very interesting upper bound in the number of, I say, look, if the graph is k critical, you shouldn't have more than this edges. Because if you have more than this edges, this graph cannot be k critical. Maybe, I am not saying that every graph on k critical has to, no. All I am trying to tell you that come up with an upper bound, and maybe there are critical graphs which touches that upper bound. That will be great. But come on, think. Okay, that's all that I wanted to say today.
So when you remove an edge, the endpoints can still be there.
Yes, yeah. That doesn't mean that the vertex cover size will not decrease. No, look at an edge, just edge. Delete this edge, vertex cover becomes 0. But like this is vertex cover 1. This is k critical graph, 1 critical graph, right? Okay. Any more question? Otherwise, I'm done.